Oman Khan, welcome you all for the fourth day of the FDP on Diagnostic Maintenance of Mechanical Systems. Without wasting much time, I would like to invite our first speaker of today's session, Dr. Jobin Varghese, who is an associate professor in Adi Shankara Institute of Engineering and Technology, Ernakulam, to share his knowledge on the topic condition monitoring of robotic joints. Sir has teaching experience of 7 years and also published around 11 research papers, out of which 5 in journal and 6 in conference. I welcome you, Dr. Jobin, sir.
I, Oman Khan, welcome you all for the fourth day of the FDP on Diagnostic Maintenance of Mechanical Systems. Without wasting much time, I would like to invite our first speaker of today's session, Dr. Jobin Varghese, who is an associate professor in Adi Shankara Institute of Engineering and Technology, Ernakulam, to share his knowledge on the topic condition monitoring of robotic joints. Sir has teaching experience of
Over to you, Jobin, sir.
Okay, thank you. I hope you can hear me, right?
Yes, sir. Yes, sir. You're audible.
Yeah. So I just thank the organizers for inviting me to have this talk here. So I hope, do we have some more participants to be joined, or shall we start the right away?
I guess they may be delayed to join. You can start, sir.
Okay. So is my PPT visible?
Yes, sir, it's visible.
So the topic which is which I'm going to discuss here is the condition monitoring of robot joints. And basically, as introduced, myself, Dr. Jobin Varghese, Associate Professor in Adi Shankara Institute of Engineering Technology under Mechanical Department. So before I just go into this one, can I just hear that how many are from electronics or robotics background? Is there anybody who is particularly from robotics background or maybe from electronics background? So you can have a chat here. And if you are from that particular background, it will be well and good where I can just discuss in detail. Is there anybody? So are you from mechanical? How many are from mechanical background? Or do you have some relation with the signal processing, that related parts? So can it be interactive? If you're from which background are you from?
Okay. Sir, all are from mechanical only.
Okay, mechanical background. Oh, okay. So somebody will be having some idea of the vibration, the analysis of vibration. So this is basically based on this particular thing, the vibration analysis. Okay, let's go into this one. Okay, conditioning monitoring of robot joints. So before I start, let me explain you. The thing is like there will be different area where we can go for the research in robot. So there are robo like the algorithms, AI, artificial intelligence algorithms that can be made to teach the robo, or even the control system. We can go behind the control system, how to control the joints, or maybe the application wise where we can go for a biped model, or different serial kind of like we can go for the serial manipulators research or the parallel manipulators research. And okay, above, so these are some of parts where we will be designing the robot. So when you compare this one, this is quite different from this one, that all these parts which I discussed in the robo research. So here is a condition monitoring of robo joint. So this is actually a maintenance field. A maintenance field where once the robo is implemented or it is being fixed for some work, if a failure occurs, that has to be monitored well in advance. So that is the agenda behind this condition monitoring of robo joints. So let me go into the first part, that is like we'll see what is by condition monitoring. So as I said, it's like a maintenance where we will try to avoid the failure in advance. So you know the production process. For example, in the industry, for example, in a car manufacturing industry, the robo is continuously welding the car parts, or they're tightening the screws, everything. And in between, if it happens that suppose a joint is not working, or maybe a gear failed, or maybe a bearing has issues, like having high friction issues, or maybe there is no fluid. So what happens is that the total robo will malfunction, and we have to stop the robo and we have to correct it in order to continue the working. This takes a lot of time. A lot of time is wasted for the production, and the total production is out, just affected. So as a result, we say like in order to avoid this type of complete failure, we will know well in advance what is happening. So okay, this way this can be done, and it will be, so this way it can be happen. Then in fact so somebody is joining on the way. So what is the idea behind this one is like we will be predetermined how the failure occurs, and accordingly we will be identifying which joint has failed, and we will be before complete failure, we will be replacing that joint, which will not affect the total working time of the production. So this is the major idea here. Now this is all like a major aim here is, as already I have discussed, the major thing is the 0% downtime in operational production line. So we don't want to waste the time for replacing the components in this one in a production line. So that is the main aim of condition monitoring. And so what we are doing is, what usually we'll be doing this condition monitoring system will be implemented into the robo, maybe robo joint. So as a result, a live session can be seen whether there is a failure happens or a probability of failure may happen. So accordingly, we can just avoid this complete failure of the system. Now it comes to the history of the condition monitoring. Now there is a slight change that happens in the recent research, and it was in the previous research, like they will be using a statistical method, for example, bathtub curve. So based on this bathtub curve, it's like we can identify at what cycle, for example, in case of a bearing, if it is running of 10,000 cycles. So in a prediction using the statistical model, like a bathtub, it can predict that after 10,000 cycles, the particular bearing can fail. There's a chance for failing that one. But there are problems with this one. There are issues with this one. That is, the major issue is that, for example, we have predicted 10,000 cycles. After 10,000 cycles, the bearing will get failed. But what happens if it failed before 10,000? For example, at 9,000 cycles, if it failed, maybe a dynamic factor come into being, or maybe an environmental factor come into being, and if it failed. So well before the predicted life cycle, it may fail. In reality, it may fail. A complete failure can occur. So that is one of the disadvantages of the statistical model. And second thing is like, in case if the prediction is 10,000 cycles, only after 10,000 cycles, the bearing may fail. But in reality, if it failed at 11,000 cycle, so what happens is that 10,000 rotations was able to do in that one, or it could have been performed. But well before that, what happens is that well before that one, we have replaced the components as per the statistical model. So this is actually when you take the cost effective design, this is actually it's not a good way. Also, it's not a best way. So as a result, the researchers start thinking of how we can monitor this one in order to avoid the complete failure. So that is the major phase change that happens in the condition monitoring. So as you know, as we have discussed, the statistical method is in fact less accurate because we have a prediction. It says that it may fail at this particular cycle, but the failure might occur before the predicted cycle, or maybe failure may occur after the predicted cycle. So, well, as we said, 10,000 cycles, it can occur at 12,000 cycles. So that is the wastage of money, also the time. So in order to avoid this one, we should have a monitoring system that is called a reactive maintenance. So the reactive maintenance, in fact, we use some sensor systems. So we will be using the sensor and we'll be connecting at the joint. With simple example, I can say, as we are going to discuss the same thing in the further slides, that is like an accelerometer. Simple example is an accelerometer. So we'll be connecting accelerometer at the joints. As a result, the acceleration developed in the accelerometer will be collected with the help of data acquisition cards. Usually we have done using the NI, National Instruments. So different data acquisition systems are there, whether we have to see the sampling rate, and based on we have to choose this one. The accuracy all can be defined based on this. So if the sensor is connected at this one, whatever be the acceleration, that can be absorbed, that can be taken into the computer using the software. So here you'll be using the National Instruments data acquisition system and the LabVIEW. So LabVIEW is the software. So using the software and the sensors, will be collecting the data. So what is the advantage is that whatever there is a variation happens, if there is slight variation happens there, it can easily be monitored. Even it is running smoothly, obviously the waves will be giving that it's running smoothly. But in fact, if there is some variation happen, that will be representing in the signals. And only next thing is that we have to analyze the signal in order to get where the defect happens. So advantages of conditional monitoring is like we can avoid the failure. The predetermination of the failure status can be made, and we can avoid the failure. And as a result, we can save maximum production time. And there is a second chance. Is that suppose there is a particular failure happens for one component. For example, a shaft is connected between two different bearings, and one bearing got failed. So what happens is that there is a misalignment in the rotation of this particular shaft, and this can cause some damage to the other bearing. That is, a related failure can occur. So because of a particular failure of one component, the other components, the probability of failing of the other components is much higher. So this can be avoided even using the condition monitoring, because we are monitoring the condition whether the joint is working perfectly. And finally, it comes to digitization and Industry 4.0. So the rules, like we'll be digitizing all the things, whatever be the condition, that will be taken as the wave, and they will be converting into the 0 ones. Then we'll be controlling, and we'll be just analyzing. After that, we'll be finding the peaks, and we'll be doing that. We'll see as we go. Okay. So as I said, the condition monitoring, the advantage is why we have to go for the condition monitoring system. Now, the major condition monitoring systems which we come across are vibration, temperature, and lubrication. So as you know, these are very important parameters which has to be studied. So if you see the case of a bearing, obviously a hydrodynamic bearing, this both comes into being, like a temperature as well as lubrication comes into being. But I'm not going into this one because it is not a common practice for a robo. Rather, we will be going for a vibration. So the vibration occurrence we can see in a rotary joints or in rotary machines. So basically it is rotating at a higher speed, the vibration will be increased because there will be some defect in the joints. The defect in the joints will create vibration. Okay, now we are trying to find out what are the defects that will happen in the joint, so that if the defects is going much higher or if it's greater than the allowed one, we will remove that part and we'll be replacing with a new one well before the complete failure. Because if it is a complete failure, it can totally affect the other parts as well. So this is a major thing here. Okay, so as I said, like three important parameters that will be monitoring. For the condition monitoring will be vibration, temperature, and lubrication for the joints. Okay, that can be happen for others as well, but in the case of in particular case of a robo, we'll be going for these three parameters. Okay, for this study or for this analysis, we'll go for a particular robo. So that is named as ABB IRB 6600. So this is a serial manipulator robo. So this is serial manipulator robo, and this is widely used in car manufacturing industry. So if you can see the Benz, obviously the Benz, Hyundai, these cars, they are in case of the Benz, they are completely automized using the robo joints, since every manufacturing, the welding, the screw tightening, the painting, all the process has been doing with the help of the robo. So there, this type of serial robo will be using. But remember, so if you have a chance to see this one, you can go into YouTube, you can search for the robo, how it's working. So as you can see, this will be continuously moving. The joints will be continuously moving here and there in order to do the task. Okay, if you analyze this robo, you can see that how many joints are there, like axis 6. So there, this comes the end effector where we will be connecting the tool. Then there is another axis. There is another axis, rotation axis here, axis 2, axis 1. So what happens? This can rotate 360 degree. Like, you know, this total structure can rotate 360 degree. Suppose if there is a work here, work volume, to define the work volume. Suppose if there's a work here, the total robo will rotate and come to this point. And if the work is here, this part, the total robo will come here. So there is a rotation that can happen. That is the axis 1. There is second called axis 2. So axis 2 means if you want to extend the legs, extend the total, what do you call the manipulators, that is the axis or the manipulators. In fact, we have to rotate this part, that is the axis 2. So what happens? The length will be increasing. The links of the robo's length will be increasing. And there are other joints which will be doing all the operations, the rotation. If you want to go straight upward, axis 3 should be rotated. So it will be going, having a height. Anyhow, when you just compare these things, the axis 2 is having good amount of work, because all time it has to go like this way, come like this way, it has to go like this way, or again, the total loading is on this axis 2. So now what we are trying to do is, like for conditioning monitoring, we'll be considering the axis 2 of this robo. So assume that there is a gear system as well as the bearing that is in the axis 2. So for rotation, the smooth rotation, the bearing will be used, and for giving the torque, a particular gear system is used in this axis 2. So we are going to analyze the axis 2 since it has multiple times of pressure and load acting on this axis. Now, assuming that the axis 2 is the where or the conditioning monitoring is taking place, I told you there will be two things like a gear system as well as a bearing system. So why the vibration generates? So we need some vibration signals. Obviously, from this joint, we'll be connecting accelerometer here that will be connected to the DAC system. And we need some vibration signals should be generated here so that we are continuously monitoring the condition of this joint. There is no complaints for the joints till now. but the complaints can generate because of the following factors. That is gear meshing frequency. So that is like gear meshing frequency is like we will be designing a bandwidth of signals, a frequency, bandwidth of frequency signal. And if this, for example, if it is spiked above that one, the frequency is going above the band. As I say, the band, in fact, for example, I can say 0 hertz to 10 hertz. That is the frequency which are considering. And I believe that 0 to 10 hertz, if there is a frequency continuously giving, there is no harm to the joints. Nothing is going to happen to the joints. So if that is going above that one, above 10 hertz, so in that cases, what happens is that there is some problem that happens in the gear meshing. Gear meshing, there is some problems that happen, and the gear meshing is not exact, and as a result, the frequency goes higher. Or even there is a harmonic can generate. So basically, harmonics means it's like the multiple of our bandwidth. So if I take 10 hertz, the harmonics can be 2 times 10 hertz, that is 20 hertz. If there is a signal, a frequency that is giving 20 hertz, then that is the multiple of my considered bandwidth. So such things can occur because of the gear meshing frequency. So if there is something wrong in the meshing. Second is the tooth wear. So that is like a continuous fatigue if happening. The tooth wear will take place, and the smooth engaging and disengaging of the teeth will not happen in the gears. As a result, the frequency will be generated. Next, like hunting tooth frequency. Basically, if there is an uneven or localized wear, in fact, that something the wear is happening on particular part itself, and there is an uneven wear happens. All these things will lead to creation of the frequency. The frequency boosting, that is away from the considered bandwidth. Then obviously there's a crack or broken teeth gear tooth. In that case also, there will be vibration signals will be generating, which is away from this one. Then it comes to gear misalignment. Obviously, if there is something misaligned, what happens is that the misalignment will cause the vibration, the eccentricity. There will be some eccentricity and vibration will be caused. Then looseness, which can be some parts are loosened or maybe some parts are missing. For example, if you are not tightening a particular, we are not tightening anything, a screw or a nut. In that case, also loosen happens, and this will lead to the vibration. Then the gear eccentricity and backlash. So basically, what is eccentricity? The gear eccentricity, that is the distance of the gear from the axis. Also, there is a slippage. If some slippage happens there, this all creates the frequency. So these are the major contribution of vibration signals to a robotic joints where it uses a gear system. So these are the chances for this one. So usually for torque generation of the axis of the robot, we'll be using the gear system, and the gear system can generate the frequency, the vibration, depend upon these parameters. Okay, let's come to the time waveform. So this is we have connected an accelerometer here that is connected to the DAC system, and from the DAC system, the vibration signals have been acquired, and this is a type of vibration signal which was acquired, and this is a time waveform analysis. So usually this is drawn like a time in the x-axis and the amplitude in the y-axis. So you can see there are some peaks here. So these peaks, in fact, shows there is some vibration occurring here. Also, you can see the peaks in the downward direction. And in the case of a mean line, if you draw, in this case, this is going to the center. And if you draw another line like this way, okay, so most of the signals are lying below this particular line. But when it comes to The other signals, you can see there is some signal which is going away from this one. Also, you can see the spikes here. And totally when we reach here, you can see there's a huge spike here. So when this all shows, there is a chance of failure which occurs. So if you can learn this curve or the signals well and good, then the prediction can be easily predicted before the failure. So as you say, each and every spikes which will be recording what is happening in the fraction of seconds from one element to another. So if the robot joint is rotating, is what happens inside the joints. If there is any vibration happens, each seconds it will be representing. So this all shows all the whatever be happening to the joint, that is recorded here. And only once we get the data, we can go for the analysis. So obviously, if there's a crack or something, some failure of this happens, then the spikes will be higher. So this is only a time waveform analysis, and in fact, we cannot do good analysis or a better analysis using the time waveform. So as a result, we will be going to the frequency domain, where the frequency will be plotting with the frequencies versus the amplitude, or whatever the frequencies, whatever what is your request. So usually we'll be going for the base as the frequency. And what are the parameter to be learned? Usually we use the meter per second square since it's an accelerometer. So that shows the y-axis, how far or how the amplitude is moving. So that will come into B. So what I'm trying to do is this is saying about the analysis, how to do the analysis. So we'll be finding some frequency. So let me say about the frequency. The frequency, in fact, which represent is like the number of signals that generated in a single second. So for example, if 10 signals are generated in 1 second, then we can say that, and there is another case, if 20 signals are generated in 1 second, we can say the second signal has a higher frequency than the first signal. Okay, so in this case, you can see there is a density of signals you can see over here. So if you take 1 second, 1 second time, and the number of signals generating, like I said, it is like a sine wave, go upward, downward, go upward, downward. So the number of signals that's generated within 1 second, if it is higher than the normal case, obviously there will be some defects will be occurring in the particular joint. The defects will be higher. The frequency, when the frequency is increasing, that straight away shows that there is some defects going to happen in that particular joint. Okay, so what we will be doing that when we see the amplitude, for example, I have identified this is the amplitude. Now what I will try to do is I will cut out this portion. Okay, I will cut out this portion. And I will cut out this portion because I suspect that there is some defect happened in this point. So as a result, so I will cut out this 2 portion, and I identify there is a peak here. Now we will be studying about only this section and what is happening in this section, because I can see a peak over here. And now in order to study further, I'll be converting into the frequency pattern. And you'll be seeing how much is the frequency here, whether this is lesser than the frequency over here, or is greater than the frequency over here, or is it same. So that what we'll do is that break down the signal into specific amplitudes where the frequency is different. So the frequency varies accordingly. Then time waveform indicate true amplitude when errors such as crack occurs. So as you said, that this is a time waveform. And when the crack occurs, obviously that is clearly showing that the amplitude is increasing, which shows the crack. And also we have to go for the frequency, how much frequency or with what frequency this is occurring. And so now I have to talk about a fast Fourier transformation. So this is the time domain, which will be converted into the frequency domain using fast Fourier transformation. So the fast Fourier transformation major thing is like, you can see that this is a signal. This figure shows that one. This is a signal. We are converting, or we are changing different signals. We are extracting actually the signals. You can see the first signal. This is one signal. This is the red one second. The green is the third one. So when you compare these three signals, you can see the frequency is much lesser in the signal, because within this time period, as it's moved, the number of signals, the number of sine waves created is much lesser. But when you compare this signal, this shows the higher frequency, and this comes to the much higher frequency. So the FFT, the major thing of the FFT is that we can divide, or we can separate the different signals according to the frequency requirement. So as you know, the vibration signal, as we are measuring the vibration signal, that will compare of two things, that is the real signal and the noise. So this is another part where we have to eliminate the noise. The noise can come because even though if there is no crack, even though if there is no defect, there will be high frequency signals will be showing, and that they are in fact a noise. So we have to eliminate the noise. How to eliminate the noise? We'll be just discussing that one. Now, FFT separates these signals that based on the frequency. What frequency we require, that will be FFT will be separating the signals, and we can go for further analysis. Then, so that is the major thing which I was saying, that particular frequency. So why I'm telling about this frequency is that for every defect, already there is predefined frequency. For example, if say there is a defect in the outer race of the bearing, or if there is some defect in the rolling element of the bearing, then the frequency will be within a range. So that is already predetermined. The studies have been already shown. So we'll be searching for that range of frequency in the spectrum, and we'll be extracting that frequency wave from the spectrum, and further we can study on that one. And further, while we study, we can understand, we will come to a conclusion that the rolling element will have some defect, or the outer cage will have some defect. Okay, so that defect can be learned from this thing. So that is the major thing of the FFT, which I have given a brief introduction on the FFT analysis. And this is the major backbone of this signal analysis, the vibration signal analysis, the FFT analysis. So that is the advantages. We can extract whatever the frequency we require, and based on that one, we can do this. Now there is another parameter which I want to introduce to, is the order tracking. Okay, order tracking. So in simple words, I can say the order tracking is like when a shaft is rotating at a higher speed. When it is rotating at a higher speed, what happens is that the frequency will also change. The frequency will be changing because, for example, if the bearing has some defect and the rotation is at a higher speed, what happens is that the bearing will be giving a high peak frequency signals, because the vibration will be much higher. So as speed increases, obviously the frequency will be also increases. But if it is rotating at a particular RPM, for example, at a 500 RPM, and if we are trying to analyze the signal, the same analysis cannot be utilized for 800 RPM. When the rotation or the speed is increased to 800 RPM from 500 RPM, we cannot use the same analysis. The reason is that one, the vibration is increased, much increased. So, class FDP. Okay, so that is the case of this one. Please excuse me for a second. So sorry for the interruption. So shall I continue?
Yes.
Yes, sir, you can continue.
So that is like what I want to say. The order tracking is like the frequency will be increasing. So we cannot analyze the both the cases. So in that case, what we will be doing that one is like we'll be giving a signal, a particular signal. For example, a sensor is connected, and the sensor will be collecting a sample of signals in one rotation. Okay, because the speed is lesser. And the same thing, the sensor, when the rotation increases, it will be collecting 2 samples in each rotation and 3 samples each rotation. So this type of things will be collecting by the sensor. So order tracking in the sense is like the number of samples per rotation. So this analysis is done in order to control the total the analysis part requires. So you can see this order 1 is equal to 1 sample each rotation, then 2 samples each rotation, 3 samples each rotation or per rotation. So order 3. So order 1 means, for example, this is running at a frequency 800 RPM. Then we will be collecting under the sensor. The sensor will be connected, and if there is a particular point on the shaft, this point, what happens is that one, if the one point crosses the sensor, that will be collecting 1 sample. When second point or when the frequency, when the rotation is increased to 800 RPM, the same point will be rotating twice. So we'll be collecting 2 different samples. So this order will be taken for further analysis. So in order to make it more clearer, you can see this is a raw signal, and the control is 30 Hertz to 100 Hertz. 30 Hertz to 100 Hertz. This is a vibration signal that will be generating from the joints. Okay. So for order 1, the order 1 is like this is rotating at only 30 Hertz to this generating only 30 Hertz to 100 Hertz, and we are recording from 0 to 1 second. That is the time period. So this part we will be taking out while generating. This is a total signal you can see when the shaft is rotating, and out of which only 1 sample will be collected for this one. Only 1 sample will be collected for this one, because we are assuming that this is rotating at a constant speed, constant RPM. So we'll be collecting only 1 particular signal. Okay, when you come to this one, you can see the frequency has increased. In this part, you can see 1 second to 2 seconds, the frequency has increased. The frequency increase means the rotation speed is increased. As a result, the frequency is also increased. And so this gives like when the speed is increased, 2 different signals will be generating. That is, we say the order 2. So we'll come in better clarity in this one, because we are just actually we are classifying, the signals are being classified based on the speed. So which class should be learned. So this shows that an f of t is carried out. F of t is carried out here, and this f of t is carried out for this second, 0 to 1 second collection signal, and that is from 0 to 100, 30 to 100. Okay, we say 30 to 100 frequency range, as we can 30 Hertz to 100 Hertz. frequency range, the signals have been collected and the FFT is carried out here. And when you do an FFT, obviously you can see that the frequency has been increased here. So while the frequency can be well seen here when you compare to when you convert into the FFT, and this suspects that there is some possibility of failure. So further studies are important, required, but only depend upon the frequency. We can see that there is a chance for failure may occur. So this is the case which I was telling, like, the order. So you can see from this part, this is the signal part, and this signal only one sample is collected, and that one sample is plotted here with frequency. That is the order. We have taken order 1, 2, 3. These are the order. So so this based on when you come to this part, second order, there will be 2 different samples will be collected, and that will be represented here. So now when you go for an analysis, this particular track order is only taken for the analysis part. When it comes to the second order, that is the speed. You can represent this as 500 RPM speed. This can represent as 800 RPM. This can represent as the 1200 RPM. So what happens? So for each speed, we can analyze for each speed. What happens is that the different signals will be generating, and so the classification of the signal based on the speed can be done in case of order tracking. So different orders are being kept and different speed, and further analysis can be made on this signals. Okay. So we say that order are constant to rotational for particular speed. For 500 RPM, there is only one order. For different speed, there will be different orders. So order numbers increases when the speed increases. That's why I told, like 500 to 800 RPM, there will be two orders. That is, 2 different samples will be collected. In this case, 3 samples will be collected when the speed increases. So this way, the signal can be again classified to different speed system. So we can analyze signals on the speed. Now, I just come to, there is a simple exponential smoothing. So this will be doing when there is the signals are totally diversified, and we don't know how to do that signal or how to control the signals. It's quite difficult to do this one. In this case, we'll be go for a simple exponential smoothing, and this is the equation for that one. And simple exponential smoothing, you can see we take Tn as the present signal or the signal which we have, and alpha is the smoothing constant. And you can see Tn and Tn minus 1, where Tn minus 1 is the previous signal. If this is the current signal, Tn minus 1 is the previous signal. So summing both things and using a smoothing constant here. So what happened with the smoothing constant is that one. The total, if it is a diversified, the total curves are diversified, that can be smoothed in order to create the particular one. And also the part is that this current signal, the Tn, is defined based on present signal and the previous signal. So if the previous signal is little smoother than the current signal, so that can be correlated together, and we'll getting a smooth thing. So these are the operations which we'll be doing before going for an analysis. And obviously, you know what is by root mean square. That is usually we'll be using in the signal analysis. That is the root mean square. If there is a number of peaks, so we have to identify the mean of that particular peak. Of a particular peak, we have to go for root mean square. So this gives the average value of the peak. So when you see the average value of peak, whatever the peak occurring the next time, the frequency, we can compare it with the average value, the current value. So we can understand that one. This is the average, and what is the next peak is going. So based on this, even with the RMS, we can understand that whether there is a failure may occur, because it should, if it is higher than, how much greater than RMS value, the standard deviation from the RMS value, the peaks are, that will definitely create some failure. Okay, these are the basic things that we'll be using for signal analysis for the robot joints, vibration signals. Okay. Next, I comes to, so I said like this is a type of gear that will be used in a cycloidal gearbox that will be used in the robot joints, which I have shown you earlier. And this is the gear. And in fact, we were telling of the defects. For example, if there is a backlash of, if there is a gear teeth has failure, all things can create the vibration. So this vibration we are measuring. And finally, since we cannot open the case all the time, we cannot open the joint and see whether the gears have failed. So rather, what we'll do, we'll be taking the external signal, which is the vibration signal, and analyzing the vibration signal, we will come to the conclusion that what happens in that. Okay. So I already told you some of the frequencies, the defined frequencies. There are 4 major frequencies for a robot joint, whether it has undergone a failure or not. So first one is a fundamental train frequency. So this frequency will be occurring when there is a defect in the cage of the bearing. So bearing has, there is a cage for the bearing, and if there is some defect on that cage, then this type of frequency, so already the plotted frequencies are there, this type of frequencies will be generated, or not exactly like this, but similar to this type of frequency will be generated if there is a defect in the cage. Then second one is the ball spin frequency. Then if there is a rolling element, similar words if I say is a ball bearing, if there is some errors on the ball, then this type of frequency will be generating. And remember that in this ball spin frequency, there will be 2 different signals we'll be getting, because if there is a defect in the ball, so that is contacting top and bottom. So the ball will be touching top as well as bottom while rotating. So as I said, there will be 2 different contact points, and as a result, 2 different vibrations signals will be generating. But in this case, cage and all, a single vibration signal will be generating. That is, we can see a repetition in this case, in the case of a ball frequency. Now, ball spin frequency. Then it comes a ball pass frequency of the outer rays. So basically, from the word itself, from the statement itself, we can say that there is some defect in the outer rays. Then this ball pass frequency, there will be the vibration signal will be generating in such a way that this will be replicating the ball pass frequency. So the outer rays defects have been already recorded and the frequency has been plotted. And finally, ball pass frequency of the inner rays. So I say, if you know, I don't know whether you know the outer rays and inner rays. So in the case of a ball bearing, the balls have been placed between 2 different channels. So the channel, the top channel is called the outer rays, that is outer rays, and the bottom channel we call as the inner rays. In fact, the ball is having some contact with the cage of the inner cage, inner part of the cage of the bearing. So that is called the outer rays. So there is some scratches or some wear happens on the outer part of the cage. What is the outer rays? If something happens to outer rays, the rotation is totally affected, and the ball will be continuously rotating, and whenever it touches that particular part, what happens is that the vibration signals will be generating. Same for the inner rays. So all these frequencies are predefined and been plotted. So when we got a signal, we'll be comparing, we'll be extracting the signals using the FFT, and after that one, we'll be comparing the signals with this fundamental frequencies. And we'll be seeing whether some frequencies are matching. And if it is matching, obviously we can right away come to the conclusion that there is a defect happened in the cage of the bearing if we found a similarity for fundamental train frequency. Suppose if you have, when you map or when you compare the frequency which we have extracted using the FFT with the predefined frequency, And if we find almost a perfect match, then we can identify what is the defect in the bearing. Okay, so we will be understanding that the bearing, the time has reached for the bearing to be replaced. If we are avoiding that signal, if we are avoiding that warning, the further what happens is that finally the total joint will be get crashed and no work will be doing, and after that it requires a lot of time, enormous time in order to correct this error. So rather what we do is that when we come to a conclusion there is some error happen here, suddenly we will be changing the bearing. So once the bearing has been changed, it takes a very short time in order to change the bearing before the failure, and we will be replacing, and the production process will be continuing. So the time is saved in this case. Okay, so I come into furthermore analysis, the signal analysis. So this is one of the method. I said you can remove the FFT, you can use the FFT, so that that particular will be different frequency signals will be extracting, and this different frequency signal will be comparing with this fundamental bearing frequencies, and we can identify the defect. So the defect can be early predicted using this method. Now it comes to some signal processing methods and statistical tools. So this, which I was telling, like we will be converting from FFT and we'll be comparing. But before that one, there are some other process to be completed, like smoothing, also filtering. So all these things has to be done before we are going to apply the FFT. Okay, we'll see into that things in this portion. So signal processing methods and statistical tools which we'll be using. So the major thing is we'll be using the kurtosis things, the spectral kurtosis here. So idea behind this one is only we'll be seeing the Gaussian distribution, of the signal, and we'll be seeing the Gaussian distribution with the signal. So so when you see a signal distribution with the Gaussian distribution, if they are in line, that is, there is no change with the signal, that the signal distribution is exactly same as the Gaussian distribution, then there is no kurtosis. The kurtosis is 0. So kurtosis is already defined as mu4 by sigma 4, where mu4 is the force central moment. And I'm not going into detailed calculation and detailed explanation of this kurtosis. So this is a usual thing which we'll be using in the signal processing. And the second case is, you can see, when you see the signal distribution with that of the Gaussian distribution. So you can see the Gaussian distribution. This signal is moving away or is being upper from the normal distribution or the Gaussian distribution. As a result, the kurtosis value will be greater than 0. So what this indicates is that the signal alignment is above the kurtosis value, and this probably a chance for failure occurrence. A chance for failure might be occurring because of this condition. And next one is kurtosis less than 0, where you can see signal distribution that is which is lesser than, as you say, which is below the Gaussian distribution. So in the case the kurtosis less than 0 is negative. So what happens here is that this is definitely a failure process. If such scenarios has occurred anywhere in the case, so we can assume that or we can come to the conclusion that the bearing is getting failed or the component is getting failed. So we have to confirm the failure or where the failure frequency in the spectrum. We have to find out the frequency that is occurring in the spectrum. That is the next case. So I hope you understand this way. That is 3 cases: kurtosis equal to 0, kurtosis greater than 0, and kurtosis less than 0. So kurtosis is equal to 0. In fact, the signal distribution is same as Gaussian distribution. In this case, the signal distribution is greater than or is the spike. There is a spike happen in the signal distribution when compared to the Gaussian distribution. And in this case, this is below the Gaussian distribution. So this is a definite failure case, and this is a probability for the failure happen in this case. So what are the advantages of spectral kurtosis? Why we should use this one in order to analyze the signals? So it's like we identify the abnormalities of measured signal spectrum from the Gaussian distributed spectrum. So you can see this one. There is abnormalities happen. There is a peak, a spike happened there. Here, this is lesser than this one, the Gaussian distribution system. So in this case, and we have given two different names like leptokurtic and platykurtic distribution. So these are the distribution names has been given. Now, so I say like leptokurtic, it's like obstruct the evaluation of the signal. So the signal evaluation is obstructed because of this one in this case, and as a result, it leads to a case of failure. And leptokurtic distribution is sign of damaging event to the object. So these two, not only these two, both are a failure cases. And here what happens is that damage will occur. Damage, in fact, the gear means the gear teeth will be broken, or there is some wear and tear happens. Something damaging happens here. And in this case, obviously, this is also a failure case, but in fact, it's not. It may or may not be a damage. May or may not be damage, but definitely this is a damage. So it's a conclusion which we can obtain from these three things. So once we identify that there is a damage happens, there's a chance for a damage happens, further we have to go for analysis, further analysis. So that is the analysis of what is called enveloping. So the enveloping is like we are conditioning the signal, whatever be the signal, the vibration signal we received from the tag, we have to condition before going for a further analysis. Okay, so you can see first we get a time waveform. So the time waveform is obtained from the accelerometer, and we are collected using the tag system. Now, what happens next? We will be applying a filter. So I hope you may be knowing this about the signals. In the vibration signals, we will be doing the same thing. We will be applying some filters. So the filters is like we have a required bandwidth, or we say that 0 to 10 hertz is the bandwidth where it will be working perfectly. So that is our bandwidth. So if there is some signals that occur at 12 hertz, that will be filtered out. That is the thing. That is the second step. And as a result of this filtering, there is a dense spectrum will be occurring with less undesired signals. That is whatever we have said, like our bandwidth. It should be within this bandwidth. And whatever be away from the bandwidth, we are removing, filtering that one. It can be a noise, or it can be the signals which we don't require. And the second step is that once we have done the signals within the bandwidth, or we have a required bandwidth at 0 to 10 hertz, we are only considering 0 to 10 hertz bandwidth, and we assume that maybe 0 to 10 hertz can be a perfect working condition, or else I can even like converge the bandwidth to 0 to 5 hertz. I say 0 to 5 hertz are perfect working, and if it going above 0 to 5 hertz, there is a chance for defects occurrence. So as a result, I take 0 to 10 hertz as the bandwidth where a defect occurrence that's included into that, and all of the signals away from 10 hertz has been filtered. The second thing is like we'll be passing the signal through a rectifier. So the main function of the rectifier is to make all the signals positive. So if there is any sine wave, there is a positive and negative movements or axis you can see. Now, when you have an absolute data, when you have taken the absolute or a modulus, or we say not absolute modulus, the absolute value of this one, it becomes as so pass through rectifier, and you can see the absolute value it takes to positive. Signal becomes positive. And so what is the advantage of when you make it as a positive system? If there is anything happens, abnormalities happens, it can be identified because that everything on the above and x-axis. Now the third step is like, in order to assure that it will be going through, we have removed all the clutters. What we are doing is we'll be passing it through a low pass filter. The low pass filter will be passing it. So the low pass filter, in sense, will be only passing the signals which we require, that is lesser than or within the bandwidth. So eliminates inner sidebands of signal required and bandwidth. So so there is a sidebands can occur that is slightly above the required bandwidth. So all the signals required that can be filtered out using with the help of a low pass filter, and no clutter will be there within the required bandwidth. Now, as we are passing through the 3 steps, what happens is that we'll be getting almost perfect signal that is good for analysis, further analysis. So once we condition the signal, we have made the signal and we have conditioned the signal by removing unwanted things and only required things. Where there will be obviously a noise will be there. Noise is not removed in this case. Only the signals, we are limited to the bandwidth. And we will be performing F of t. So F of t is exercised. And what we'll be identifying, so we'll be separating different frequencies, whatever the frequencies you require, we'll be separating and we'll be finding the fault frequencies within the spectrum. And also we'll be finding the location of the fault frequency. So these are the things which we'll be doing in the enveloping system. So first thing, as we say, we go into the kurtosis analysis, spectral kurtosis analysis, and we'll identify there is a damage, a system, there is some damage is happening there. Then we'll go for the enveloping, and we'll be just separating the frequencies in order to having further studies. Next is like a spectral autocorrelation. Okay, this is another way. So this is another useful way where we can easily identify the noise. So in this case, what we have done is like we have separated the signals in order to have a further analysis. And in this case, the spectral autocorrelation. So let me say that we'll be using a third medium here. Okay, in this case is so here what you can see, this is a signal, and this is the same replica of signal. Okay, one signal here, same replica of signal. Now this signal is passing through this one. Now as we say, you can see this is out of phase. This signal is totally out of phase to the signal. They are not in phase. And we have a third screen that is a correlation screen. All right, correlation graph. Whenever the signals are well correlated, the graph will be showing the correlation results. And what we are trying to do here is that if there is a useful signal, for example, there is a chances for the defect as well as the noise. Okay, the defect can be because of the outer rays defect. And when it's rotating, the defect signal will be repeating. That is the assumption here, which we'll be using here. The defect signal, the vibration signal, defect vibration signal will be repeating itself. And the noise signals will not repeat. The noise signals will not repeat. So these are the two different graphs. So assume that I'm taking this directly collecting from the sensor. This is also directly collecting from the sensors. These are not pre-recorded things. We are collecting from the sensors. and we are trying moving this one to this one, like this one under this one, like the first signal, second signal is moving below this one. So whenever it is under phase, under or in phase, so you can see when they are in phase, the correlation value is increasing, it's peaking. Okay, whenever they're in this area, as this is a movement, this is the first stage. The stage it is moving here. You can see the correlation signal. When there is no correlation, you can see the correlation has been going downwards. We're assuming that a noise is happening here. There is a noise here, and this when it have some in phase or they are in phase, then what happens is that there is a correlation graph is increasing, which gives the highest peak here. So through this way, there is further graphs which shows. And in this case, this is a perfectly correlated condition. This is a perfectly correlated condition. And you can see when it is, as the signal was moving from here, started from here, it moved to an first it has entered these two parts, then the correlation increased. And when it was, so that was the peak, which was this peak was this peak, okay, this peak. And further, when it's totally correlated, again the peak has increased. Then you can see after that the signal is moving in this side, and as it's moving, you can see a similar peak is obtained here, two peaks here. Then it is going out of phase, and correlation is reducing. So this is the highest peak you can see, which happens during the perfect correlation. So this is the second half, and this is the first half. First half, you can see first half it is moving like this. Second half it is moving. Now the the correlation which clearly shows here clearly shows that there is some, whenever there is a noise happens here, the correlation does not give a good value. So this part is a noise part, this part is a noise part, where this part is a signal part. So the signal part is that there is some, if there is a defect happens, that also gives the signal, because there will be in phase. Okay, whenever there is a defect, that will be repeating as the rotation is continuation, that will be repeating, and the repeating ones will be in phase when the signal pass like this way. So as the repeating one is in phase, what happens to that one is that that gives a signal. So if we are suspecting that, for example, as we have started here and we identify that there are some errors here, and we are suspecting that there is some error here, what we will be doing is like, we'll be extracting this part. Okay, extracting. Okay, we'll be extracting this part. So we assume that there is a synchronization or the in phase happen for the signal here. We'll be extracting this part. Then we'll be going for further analysis in order to find out what error or what damage or what defect is occurred in this one. Okay. So this way, this is called the spectral autocorrelation. So for spectral autocorrelation, what we are usually doing is that the two steps are there for the spectral autocorrelation. That is, the first one is the correlation. That is the correlation which we are doing here. So I say spectral autocorrelation comprises of autocorrelation and FFT. So autocorrelation is this one, like we'll be correlating, we'll be moving the signal over the same signal, and we'll be having a correlation graph. If the perfect correlation shows as it moves here, then it is called the autocorrelated. Okay, autocorrelation, and the autocorrelation which clearly shows that the correlation have a higher peak, which shows that they are in phase. The signals, the defect signals are in phase. Now, the total you can see once after this movement the signals are separated, and the total graph is shown here. So you can see there is no correlation. It comes here, slight correlation, then a noise comes here, slight correlation, then a perfect correlation, then again it's repeating this part. It's going and going like this way. So they are like the total correlation can be obtained from this one, and out of which what are the signals and noise can easily be found out from this. It's a case of condition using autocorrelation. Once the autocorrelation has happened, we'll identify next will be doing the fast Fourier transform. Fast Fourier transform will be applied. So then you can see 3 repeating so there is 3 repeating signals which are 6.25 Hz and 7.5 Hz. So we are extracting those frequencies. So that particular frequencies are extracted because we only want to study about that frequency, what type of defect is there. And once we get the frequency and we compare it with the different frequency in order to find out what type of defect is occurring. Now we get 3 different frequencies, that is 6.5 Hz and 27.5 Hz repeating frequencies. And these repeating frequencies are the defect frequencies. So what we are going to try to do is that we'll be taking this one and comparing it with the time wave analysis. Is the frequency spectrum of different repeating frequencies, and will be Can you hear me?
Yes, sir, you're audible now.
Okay, have I missed the class in between when the connection has gone?
Yes, sir. Before 5 minutes earlier, you had left.
Okay. It's like something happened to the connection.
Yes, sir.
So that's all about my presentation, and really I thank Dr. Rupesh for inviting me into this one and take a session on condition monitoring.
Okay, sir. Thank you, Jobin, sir, for sharing your knowledge on condition monitoring of robotic joints. Now, I request our participants to clear their doubts with Jobin, sir. Participants, if having any doubts, can clear with Jobin, sir. Okay. Thank you very much, Jobin, sir, for sharing your knowledge.
Thank you.
Thank you, sir.
Thank you, sir. Thank you.
Thank you.